This is a pre-lab mini lecture to help you think about conservation of energy, which will also be in the lecture notes later this week. But basically, conservation of energy tells us that if you have a certain amount of energy of motion, which we'll call kinetic energy, and we'll talk about what energy is later, at some point, and you add it to potential energy, which is energy associated with position, which we'll also talk about, and you might have seen it before in chemistry, that quantity is conserved, meaning that it's the same there as it is at another point in the maybe in the falling of an object, where you're converting kinetic energy, which is the energy associated with how fast it's moving, with the potential energy, which is the energy associated with its position. What it's saying is that that total remains constant, assuming there's no loss due to heat, which we're ignoring. And so that's what this lab is going to be about. And in class, we'll talk about equations for kinetic and potential energy, but I'm going to write them out here. Kinetic energy, the energy of motion, is equal to 1/2 mass times the velocity of an object squared. So if we're talking about the kinetic energy at position 1, I'll say that that's associated with its velocity at position 1. And an object has mass m, so I'll just put the m in there. The potential energy is the energy associated with the height of an object. The higher it is, the greater its potential energy. You can think about it like that. And I'm going to call h1 the height of an object at position 1. And v1 is the velocity of the object at position 1. In lab, that initial velocity is going to be 0. It'll make our equation even easier. Add those together, and you're going to get that that quantity has to equal the kinetic energy at position 2 plus the potential energy at position 2. All right? And we're often going to take the potential energy at position 2, which is like the ground, to be 0. Or the final position of the object, we'll often take that to be 0. It'll make things easier. So I'm going to make what we're associating 0 in lab 0 here, although it's not always that case. I'll say, okay, that's 0. And I'll say, okay, that's 0. And what that gives us is that mgh1 equals 1/2 m v1 squared. And I'm going to cancel the masses out. And if I solve for the velocity, I'm sorry, this should be v2 squared, not v1 squared. I apologize. I'm interested in finding what the final velocity of an object is. That final velocity, or v2, is going to be equal to, well, I multiply both sides by 2, and the masses cancel, of course, so it's 2 times g times h. v2 squared, so v2 is equal to the square root of 2 times g times h. All right, so that gives you an equation that you can use in lab to find the final velocity of an object that slid down a ramp. And h is the height that the object drops. So if an object's on a ramp, the height that it drops is the height of that ramp, like that. That's the h we're talking about, which makes it very useful. So we're not talking about the distance along the ramp that the object moved. We're actually talking about the height it drops. It's going to be a really useful concept for us. All right, in the lab, it asks you a couple of pre-lab questions to get you thinking about conservation of energy and what you can do with it. It's assuming you have a ramp 2 meters long and that it's suspended by a block that is 2 centimeters tall, right here. And the question then is, how much does the block drop? How much does the height change if you were to go not 2 meters along the ramp, which is the whole way down, it would change 2 centimeters, but just a ½ meter? What is the difference in height, or the vertical distance that the object here drops in going a ½ meter down the ramp? And so what you can say is, okay, that ½ meter, the ratio of that height that it drops to a ½ meter is equal to 2 centimeters divided by 2 meters. You can use similar triangles here. This there's a little triangle right here you could say is similar to the bigger triangle there. And from that you could figure out that this height that it drops is just simply a ½ centimeter in this case. All right, so that's pre-lab question 1. So what would the velocity of the cart be if it dropped to here? And let's use the equations of conservation of energy, the one I just gave you a moment ago. That equation, if you remember, is V2 is equal to the square root of 2g times h. Well, it drops a half centimeter here, which is equal to 0.005 meters. So let's plug that in, and let's just say g is equal to 10 meters per second squared for now. All right, and let's solve for V2. Okay, V2 is equal to the square root of 2 times 10 times 0.005. All right, so let me do the math here. V2 is equal to the square root of 20 times 0.005. Let's see, 0.05. This gives me 0.2. If you do the math there, I think, let me see. No, I take that back. 0.1. Yeah, 2 times 0.05, let me write that out again. Square root of 0.1 meters per second. So let's use Excel and find what the square root of 0.1 is. Okay, square root of 0.1 is 0.31 meters per second. All right, so we would expect our cart to be moving at 0.31 meters per second when it drops that half meter along the ramp. So that's how fast it's moving on the ramp, just by knowing how far vertically it drops as it's moving along the ramp. Now I'm going to do the same thing using the conservation of energy. Using the equations of kinematics that we've been using all semester. We need to find the acceleration in that case. It's a little bit more of a task, but we should get the same answer whether we're using conservation of energy or the equations of kinematics. So I'm going to do that next. Using the equation of kinematics, I'll use this equation. It's familiar to us. V final squared equals V initial squared plus 2a times x final minus x initial. Keep in mind, I'm not using g here. This isn't free fall. It's kinematics. It's a cart rolling along a track. Acceleration is not negative g. It's the acceleration of an object on a ramp. Remember, this is a ramp. Acceleration is g sine theta. So let's figure out what sine theta is. We could figure out what theta is and find the sine of it. One way to do this is knowing this is 2 centimeters and this is 2 meters. The hypotenuse is 2 meters. The vertical is 2 centimeters. Theta is that angle there. And I could say, using SOHCAHTOA, sine of theta is equal to the opposite side, which is 2 centimeters, divided by the hypotenuse, which is 2 meters. If you take the ratio of those, you have 0.01. That's the sine of theta. I don't even ever need to find theta. I could find theta, take the inverse sine of this, and then take the sine of that, and I'd be back to 0.01. But I don't need to do that. So the acceleration then is going to be equal to g times sine of theta, which is g times 0.01, which is equal to 0.1, because I'm going to take g to be 10 meters per second squared. So the acceleration of the object on the ramp is 0.1 meters per second squared. All right, so that's the acceleration. I can put in this a right there. And my initial velocity is 0, remember? So let's find my final velocity now. My final velocity, using the equations of kinematics, is equal to, or my final velocity squared is equal to 0 plus 2 times a, which is 2 times 0.2, times the distance I moved down the track, which is 0.5. And if I do the math here, I'll have to go to another page, but 2 times 0.2 is 0.4 times 0.5. Let me see if I get this right. Whoops, it should be 0.1. Sorry about that. My final velocity squared is equal to 0 plus 2 times 0.1. My acceleration is 0.1, it's right here, times 0.5. 2 times 0.1 is 0.2, times 0.5 is 0.1. So this should look familiar here. The final squared is equal to 0.1. It's going to be meters squared per second squared. Take the square root of both sides. And you get V final is equal to 0.31 meters per second. This was using kinematics. And notice we got the same answer whether we use the kinematics equation where we found the acceleration, or whether we use conservation of energy, where we're looking at the vertical distance that the object drops. Both give us the same answer. The biggest issue I've seen with students doing this problem is units. Make sure that you know that your drop is in centimeters, convert that to meters, and this will all work out. Try it. Make sure you know how to do it both ways. All right. Now for the lab.